My name is Carlo Quick. I'm a software engineer in Tokyo, Japan, and today we'll be building a minimal rootless container in Rust. Okay. Today's talk is inspired by my personal project, Bento, which is a container runtime in Rust. And even though I'm not talking about my personal project today, by building a minimal rootless container in Rust, I'm allowing you to have like maybe a small snippet into my journey into containerization and the Linux kernel. I'll show at the end a little bit of Bento at the end, but that's for later. Okay, so today's talk, the goals are to cover container fundamentals, give you the Rust tools to build your own, and a sense of why Rust makes, working with the Linux kernel more approachable. Okay? So when we talk about containers, we talk about isolation, right? And to get a feel for what containers are, we have to compare it to, of course, something a bit more well-known, virtual machines. So virtual machines are machine-level isolation, right? We have your hardware, hypervisor, which is going to chunk up, CPU, memory, and other stuff. And then we're going to have an entire guest operating systems, right? So that's great isolation, but it's also a little heavy because you have multiple guest operating systems on one machine. So again, virtual machines are machine-level isolation. Think of containers. Containers are process-level isolation. You have your hardware, you have your host operating system, kernel, container runtime, which is going to maintain the container life cycles, and you have your applications. As you can tell, there are no guest operating systems. That's because they're going to share the same host operating system, which is going to use the kernel to create and maintain these containers. So again, virtual machines are machine-level isolation and containers process-level isolation. So how does Linux kernel allow us to do that? Well, we have namespaces and C groups, fundamental components of processes. A namespace is going to control what a process can see, okay? And C groups are going to control what a process can use. So think of it this way. Namespaces are going to give you, let's zoom out. All right, there we go. Namespace is going to give a process a view of things like PIDs, host names, file systems, and C groups are going to keep it from eating all your resources, okay? So today's talk, we're only going to focus upon namespace isolation. C groups are very, very important, but that's a whole different talk. So just today, namespace isolation. Each process has its own namespace subdirectory, where we can see namespaces for its PID, network, mount, UTS namespace, IPC, user, C group. And you can tell here from my image, if you can see on yours, but I can't see it up here. But I get a process, I sleep it, I go in, I can inspect its actual subdirectory, NS, and we see here all the available namespaces for that process. We'll be using these to isolate our process to become a container. Now, I'm talking about rootless containers. So what's the root problem? Well, traditionally, container runtimes will, run your containers with root level access. And we are building containers, that have a restricted view of the system. So then we think, okay, what privilege does a process actually have when we create it with these traditional systems? Take, for example, I have an image. No, there's no image. All right. Oh, here it is. You can't see it, but sorry. So by default, without any special configuration, Docker engine, for example, will create your containers using root level access. And it's really tiny. If you have the slides in front of you, you can see it. But I create a container without any, configuration, a BusyBox container. I check within the container, who am I? I am root level access outside the container, right? That sleep process I have up here is running on root, right? Why is this a big deal? Well, because if this process were to break isolation, then it would be running on my machine as root, which of course we don't really want that to happen, right? So rootless containers. Rootless containers run as an unprivileged user. No root required. And so if your process escapes isolation, it's still you on the host, okay? Smaller blast radius, safer by default. Okay, so why Rust? Rust doesn't invent new container primitives. It doesn't replace, Linux syscalls. So why in Rust? Why are we talking about this in Rust? For me, in my opinion, Rust gives you compiler-enforced honesty. So fallible operations return a result, right? Unsafe operations explicitly marked the boundary between safety and dangerous is visible in code, right? The language doesn't let you gloss over, the difficulties of working with the Linux kernel. You zoom in. See that? Okay. So we'll be using the fork syscall later in the build, but it's going to create a new process, copy the last one and call the child process. So in C, calling fork, just calling fork, right? Nothing special up there. Then you have your switch case, right? And you actually have to explicitly handle, the error or the success or default, right? What if you forgot as a developer to do the -1 case, right? Could be pretty bad. But in Rust, using the nix crate, which we're going to see in a little bit, marks it explicitly unsafe, saying, hey, this is risky. You now assume the responsibility of calling fork. And from Rust, if you didn't handle your error case, if it requires one, it won't compile. So Rust is allowing us to work with the Linux kernel and making it way more approachable, right? And to me, more readable. But, that's just my opinion. So today's tools that we're going to work with, just one crate besides the anyhow crate. We're going to work with Nix crate, which is short for Unix. It wraps low-level libc calls into more idiomatic Rust. So for example, you see up here, getting a host name in libc versus getting a host name in Nix. It's more idiomatic, just returns a result of an operating system string, and it's just better, right? So again, kernel is still the kernel, but the boundary is more visible, and you got to handle it. So finally, let's start building. This is just for the slides. I'm going to post the, well, you have the slides already, but I'm going to also give you a GitHub link later with the actual code in it if you ever want to try it yourself. There's some things that you have to do to make sure it works by AppArmor, allowing for unprivileged users to, manipulate the user namespace, 2 dependencies anyhow, and the Nix crate. Let's do this. All right, so I'm using present term to do this. It's actually running Rust script in the back and actually running this code that we have up here in our slides. So in the back, we're seeing some stuff printing out. That's what it is. Don't think I'm just like I don't know, printing stuff and saying it works. There's actually a print function that's going to print out what we're doing behind the scenes. Just for simplicity, I'm not going to include it, but just know it's there. Print process information. Here's our roadmap for today. 1, we want a rootless container. 2, we're going to isolate the host name. 3, we're going to get PID 1. So it's going to think it is the machine. It's going to think it's the first PID in the entire thing. then we're going to isolate the root file system and think it's actually at root. So going to go ahead and do a process baseline. Let's run this. All right, cool. So small snapshot, just on my machine, UID 1000, host name, current PID, and then current working directory, right? So all 4 of those things should change to make ourselves a rootless container. So let's try and do something containery, right? Let's just try and set the host name. Let's change it to my container. No permissions, right? I can't. I'm not running sudo. So how do we fix that? I could run sudo, could run as root, change the host name, but we wouldn't have a rootless container. We're not going to run this with root. So first thing we got to understand is unshare. Unshare is going to disassociate parts of our process's execution. Well, yeah, it's right there. It's going to disassociate parts of our process execution context. It's going to take a flag argument, clone flag, and we're going to specify which part of that process we want to have unshared. Today we'll only be using these 4 clone flags, these unshares. We're going to do a new user namespace, new UTS namespace, new PID namespace, and new mount namespace. Okay, here we go. So first we're going to print our process isolation, see what it is. We're going to unshare the new UTS namespace, hopefully get the ability to set a new host name for this process. Still can't do it. We still don't have access. We don't have the privileges to do so. So now I'm going to go rootless. So there's a lot of stuff, but going rootless, we're going to rewrite that process's UID and GID maps, right? We're going to get our current UID, our current GID, and we're going to map it. I need to back up. Yeah. And we're pretty much, all this is saying is we're going to give this process, we're going to let the kernel know that, hey, we're going to run this as root, but here's my UID, so you know who I am when I try and run it, right? So we're going to go ahead, we're going to set the new UID, we're going to do the GID, we're also going to set deny to set groups, which requires the kernel is required by the kernel before it accepts a GID map to prevent any sort of privilege escalation. So we're going to go ahead and write that. So here we go. We're going to write to its mappings. Then we're going to, unshare our new user namespace. We're going to then write to our mappings, and then we're going to hopefully set that new container name. Yes, we got it. Right? So UID 0, I'm root within the container. I set the host name. So now instead of end of the world, it is called my container. And we still have to worry about the PID and the current working directory. So we got a little bit of isolation. Let's make sure and check that the host name on my machine has not changed. Nope, it's the same. Right, so now we are rootless, and we were able to set the host name for that process. So 2 birds with 1 stone. Whoa. So we're rootless, we isolate our namespace. Now we gotta go PID 1 and isolate our root file system. Zoom in. Any questions so far before I keep going? That's like the halfway point of the build. Questions? All right. Linux, so Ubuntu.
Which operating system does this work on? Is it or just for
Linux kernel?
Yeah, please repeat the question.
Oh, sorry. So which operating system would be the Linux? So we're using Linux kernel because these things are available only to Linux kernel. Right. Okay. So let's do the same thing. Now we're going to do our PID namespace. So same stuff as before, but now we're going to unshare our PID namespace. it's not going to work, just a little heads up, because when you unshare a PID namespace, the next forked process will get that new PID one that we're hoping for. So we're just going to do it anyways, just to see that it doesn't work. Yep, same PID as before, right? So let's go ahead and revisit that fork from earlier. So again, do our fork, just unsafe, get our error, and then we will have our new process that has PID 1. So a few more things we're going to add to our code is a child function that we're going to move our unshare of the UTS namespace into the child function, and then within our fork, right, which is going to be below unsharing our user namespace and PID namespace, we are going to have our fork. Parent is going to wait for the child to finish before it exits, so main is going to wait for the child. Child is going to unshare our host name, and let's go ahead and run it. Oh, sorry, next one. All right, cool. So same, that's all of our code so far, right? Rootless, PID, so the next fork process is going to be 1. I'm going to go ahead and do all that stuff to see how it works. Nice. So we went from UID 1000 to 0, so we're rootless. Host name is now my container. PID is 1. The last piece of the puzzle is that current working directory. We need to mount a new root file system. Because so far, by doing this, we've been using my own machine's root file systems. We've been using my ls, my, my bin, all that stuff on my actual machine. So we actually want to now give this container its own root file system, right? So here I'm just giving you a little extra code. We're actually going to inspect what the child can see. So I'm going to pass it some arguments, and I'm going to call those arguments. Exec is going to replace the current image with whatever that is. So in this case, ls. Is make sure nothing else there. Yeah, it's good. I'm going to go ahead and run it and see what this process can see. All right, so this process can see everything. We don't want that, right? It can see everything within my presentation, my assets, everything in my build, all my entire presentation sees everything. We don't want that, because we want it to be containerized. We want to see, you know, whatever we want this container to see. So we want to get rid of this. We want to change, of course, the root file system, which I have a minimal one here on my machine under talks, root fs. It's a very minimal Linux root file system. It's busy box. So now we're going to tell this container, hey, this is now your root file system. Don't look at mine. Look at this one, okay? So now our child function. It's kind of a little bit beefier, right? Here are just some stuff giving it the new root file system, right? So child's going to do the same thing, besides now we're going to actually mount a file system, right? We have our new UTS namespace. We're going to isolate it. Then we're going to unshare a new mount namespace, and we're going to give it root file system, the location for the container, and it's going to be a bind mount. And then we're going to change this processes, or this container's root directory. We're going to say, hey, your root directory is now where I say it is, in this container directory, where we are mounting our root file system you saw just a second ago, the busybox one. And it doesn't have a current working directory anymore, so we have to give it one. You're at, root, okay? And then we should have, hopefully, the finish line, right? We go rootless, down the beginning of main, isolate the namespace PID namespace, excuse me, fork, give it ls, I'm going to do a new host name, and then unshare the mount namespace. Lovely. we have a container. Yay! Right? So it's rootless, new host name, PID 1, and it thinks the current working directory is root, and for that, its root has that root file system that we just shared with it from BusyBox.
Question. Do you know, can you drop the write permission?
Can I?
Or when you have your file system, do you know if there's like a way to, I know you can drop like syscap and like,
Yeah.
do you drop writes?
So when you go, can you drop write permissions? So what you're going to want to do later, when you get more advanced, you're going to do an overlay file system. We're going to give it a lower one that says, hey, this is read only, which is going to be the root fs that we just saw. And everything else, we're going to give it a work directory, and we're going to give it a lower directory. We're actually going to mount, stuff from the image and stuff like that. So yeah, we will. We'll have to indicate that.
Did the LS say that's muted? Is that a BusyBox?
Yes, exactly. So the LX which is the LX that it executed, which LS was that? Was that on my machine, like my root file system, or was that on the BusyBox one we gave it? That's on the BusyBox one. So when I ran LS, this is what it saw. And it's from its, what, is it bin LS is where it gets it from? Right? So yeah, that's the one we just gave it, the new root file system we just gave to it. So we have a container, right? Not the greatest container, but hey, it's a container. It's isolated, right? Yay! Woo!
That was it done.
Hey. So we built it in Rust. If you saw the whole thing, it's less than 100 lines of code to do it. A lot of that is just the process printing function I have there. But we did it. We built a container from scratch in Rust. It's rootless, right? It's a isolated host name, PID 1, and has its own isolated root file system. Linux namespaces, fork, and Rust. That's all we needed, those three things. Right? And so this brings me to Bento real fast. Just want a shameless plug of my own project. Bento takes OCI spec images from Docker Hub, isolates the namespace, implements an overlay file system, copy on write layers. Let me go ahead and show it really quickly. It's super fast. We got to pause it throughout. But so my commands: create BusyBox container with the image BusyBox. Come on, work for me. All right. So create the container. Come on, what happened here? Come on, VLC. Check its status. Okay, created, no PID yet. We're gonna go ahead and start it behind the scenes. So behind the scenes, right, who am I? Me, PID, current working directory. I started behind the scenes, so my status is now running. Here's a PID, and I'm gonna exec into it and give it the command sh, running root. Check out what it actually sees. Today, okay. So it's root, PID is 2, and its current working directory is at the root level, and I can kill containers and remove containers in Bento. I'll just let it run. I just slow it down because it's too fast. I'm not sure what it's not doing, but it'll do it. Cool. Today. Okay, there we go. That's completed. And that's it. And completed. Yes.
Any surprises as far as networking, vice pass through, sys proc file systems, sorry?
Big question. So any surprises with network pass-through, sys?
Networking.
device pass-through,
Sorry.
proxys, etc. There were lots of surprises. Lots and lots of them. I'm not sure how to answer that. But
I'm just wondering, like if I have a particular thing I want to do, are there things I can't do right now, but the way Bento is?
so Bento in its current state, you're asking what limitations there are to Bento in its current state. For the biggest one is that it only controls namespace isolation, so I haven't gotten yet to C groups. So it can kind of run wild on your machine a little bit right now. It's only an educational project. I don't actually have a thing where I'm going to be implementing. Oops. Next. So my future plans are for C groups. I don't have network namespaces yet. And I want to actually split Bento into 2 crates. I want to have the Bento D, which is going to be the daemon, and then Bento itself to be able to be the container runtime. And not have it yet, but pseudo terminals. So that's the one thing. For example, if I were to create Bento with sh, right, being its first command, it will kind of has an error because there's no pseudo terminal. So I have to actually close that terminal and exec into that container to be able to do anything with it. So yes, there are limitations. It's only an educational project at this point. But yeah, yes.
So I watched somewhere and we're using Bento, something called Bento.
Oh, really?
Yeah, so we're near like it's a reasonably large company with AI in the name.
Uh-huh.
Buddy, and
Oops.
I'm trying. Yeah,
It's not my Bento, I don't think. I only have a 23 stars, so. That'd be cool if it was. Someone needs to holler at me, but.
let's read more. Top 25.
Okay. I searched that name pretty thoroughly, so maybe someone does have it. I don't know.
It's like an internal project.
Oh, that'd be. I don't know. Yeah.
I don't know what I don't know which I have put. Some guy I've read it or pre-read.
Okay, I don't know. But yeah, that's Bento heard here my reference. Yes.
Do you know what would happen if you can do some sort of like volume melt and then native operating with file system to the container? Wrote the new file. What UID would that show up under?
Good question. What? Yeah. So if you were to create a new file, you're saying, yeah.
Yeah, essentially, like it's just like what is that mapping from container UID to the native operating system?
Yeah. So if you were to create a new file under the new UID, like in the container as root, what's that mapping? That's a very good question.
Yeah, and for volume mounted.
That's a good question. I don't know how that would be handled.
I was just because I was thinking. My question was like this in Docker. I guess one of the worst is you run a Docker dev container, and then we volume mount the repo. But unfortunately, because technical reasons, so we start over. So I think it's funny. There we go. Okay, let me start with the beginning. So I guess my question was that interesting problem at work, and I imagine other places run into it, is you have a dev container for your repo, and then you start the container, you volume mount the repo into the container. But for technical reasons at my work, we have to we're running the Docker containers with super user, and it'd be cool if inside the Docker container was super user, and then outside it was just normal user. And it'd be cool if like there'd be some sort of mapping that would just make that all transparent. So outside of it, files are handled by normal user, and inside of it, files are touched and handled by a super user. I don't. Anyway, just a thought that.
Okay.
Really cool project here. Sort of.
Thank you. I do know, like for example, you said that you can run containers as root. Docker engine just a few like super simple configuration to make them run rootless containers, but it's not default out of the box. You still have to like go and understand what rootless is and make them, so you don't have to actually run them as sudo.
Yeah, well, so to add more to it, maybe it's just a matter of I need to look into this, but part of the complication is it's like running in Minikube and then launched by Helm, and it's this whole stack of things that I'm honestly not an expert at. But anyway, I thought I'd bring it up because I just think your project's really cool because it just sort of out of the box is trying to advertise this layer of safety, which I hadn't really thought of in too much in depth.
Yeah, thank you. Yeah, okay. Thank you.
Yep. So just so you know, the IDs of users and groups. I really just
Yeah, I think so.
question I'll look too. There's another library called PRoot, which does the same thing. So it actually lets you start as non-root, but inside simulate groups. And so for the user permissions, they you can save as an extra file, and so when you go back in there, it still keeps user IDs. So everything's still running as non-root, things that's running as root. So it can still save those user IDs out of that day. Yeah, and also just so folks know, user IDs and group IDs are manually settable regardless of if the group or the user ID exists on the system. What we do is on CI, we have a specific, I think it's like 65,000 for something like that. And we just said everything inside the container is almost by 65,000. And we use that everywhere. And we statically set it in all of our images. So therefore, it all just kind of works. So yeah, you can, you don't even have to go through like mapping. There is PID mapping that happens in a container. Like root in the container is not root in the operating system. There's a map there. If you check out sysdig, which is free to install, csysdig is the command line. It does this whole like container jumping between cgroups and namespaces and all that. But anyway, long story short, you can statically set that somewhere as like a first try in CI, and then it'll just be the same in all of your containers.
Very cool. Thank you.
Anything else?
Okay. I actually do have a little bit of extra time. I had something else I wanted to do really fast. I have time, correct? Okay. I want to have a quiz.
Let's see. Cell phones?
Cell phones, or laptops. Go ahead and start it. There we go. So either go to kahoot.it. I think it's also going to give you a QR. So what's at stakes here? Big stakes. I'll let you guys do that first before I walk over there. Nice. So what's at stake here? Top number one question answerer, number one person gets a shrug sticker, holographic one, laptop sticker, the shiny. And then number 2 and 3, shameful non-shiny shrug stickers. Wow. Right? That's what's at stake, laptop stickers. I'm gonna go maybe 30 more seconds. Anyone need time at all to get in? Anyone need time? 10 seconds. 6, 5, 3, 2, 1. Can I start? All right, here we go. Oh, yeah? All right, here is it. Here we go. We're starting.
With 50%.
All right, first question. Containers provide which type of isolation?
Motion.
Emotional isolation. machine level, process level, C level, sandwich level isolation. I wonder which would be. I'm going for sandwich level. 2. Nice. 2 for sandwich level. It's opinion based, I guess. All right. Yes. Process level isolation. Containers provide process level isolation. Next question. Boom. Also, I think Wi-Fi speed is the differentiator here too.
Let me see.
Namespaces control what a process can, pancakes, use, hear, or see. Namespaces control what a process can, pancake, use, hear, or see.
Sure.
Yeah, definitely. C. Nicely done. I was obviously pretty hungry when I made this quiz. Pancakes the same with this, so.
Oh, that's on. Go Ben.
Go Ben. Next question. Compared to C, how does Rust handle risky syscalls like fork? Prevents you entirely from calling them. It allows you to eat more chicken. It forces explicit error handling via result and match. It replaces them with safer alternatives. Yeah, again, I was pretty hungry. Forces explicit error handling via result and match. Boom. What type does fork return? Result. Fork result. Option PID. I32. Unsafe IDK. Hope you're paying attention to my code up there. Yeah. Oh, who's this Alex? Alex cooking. What makes Rust approachable for Linux kernel work? Safer syscalls than C. Dangerous boundaries more visible in the type system. It hides unsafe operations behind bars. Replaces the kernel C interfaces with Rust ones. It makes dangerous boundaries visible in the type system. Who won? Who gets the shiny? Shrugs.
Jack.
Oh, you got non-shiny. Jason, non-shiny. Who gets the shiny one? Alex. Very cool. I'll get you guys during the break, by the way. That's it. Thank you very much.
Thank you, Carlo. Round of applause, please. Okay, let's take